Welcome to the school. I'm Matteo Massironi from Padua University. I'm teaching planetary geology, and together with many people that you will meet during the week, I funded with Riccardo, Luca, Barbara, and many other this school 5 years ago. And my duty today is to explain you what geological maps are and which are the frontiers of geological mapping on planetary bodies. And so geological maps, since this is the first geological map that you see, the modern geological map, it was done in the 19th century by Smith. And since the beginning, the geological maps were very important, and they are important for science investigation. They were important for resource and mining exploration, evaluation, exploitation, management of the resources, hazard and risk assessments, land use infrastructure planning, and environmental protection. These are the main reasons why geological maps are done on the Earth. But the same reason are for planetary body, because science investigation are important, resource and mining and resource evaluation exploitation are important for future development of outputs on planetary surfaces. Hazard and risk assessment are important for landing and traverses, and even the land use and infrastructure planning, again, for the future, future human settlement on planetary bodies. And environment protection is actually a way for, I would say, a way for not, we say, to take care of the source of your planetary bodies in order not to bring back potential hazards or pollute with biological pollution, our biological pollution planetary surface. And this is actually called planetary protection. So all these main points are important for planetary geological mapping. The things are different for planetary mapping on, I would say, geological mapping on planetary bodies and Earth geological mapping. And actually, any geological mapping on the Earth has to take into account the three main processes forming the geological history of planetary bodies, and in particular of the surface or of a landscape. So at the beginning, we have the sediment deposition, the deposition on different units on top, one on top each other, which is it forms, the formation process. Then we have the deformation process. And at the end, we have the erosional processes. And all these kind of processes are actually repeating through time. And by looking to a geological map, it will be important to understand which are the different processes that were important, and which is the geological history of forming, deforming, and shaping. So deposition, deformation, and erosion. Looking at the landscape, this is a landscape on the Dolomites, Cimon della Pala. And you see clearly that you may see all these kind of processes. The first one, it's the formation different geological units, one on top of each other, and you actually see the sediments going and the stratification going one on top of each other, as you see to the left and even to the right. If you follow this stratification, you see that it is deformed by faults. So we have the deformation process that it's visible on the landscape. And if we look at the boundary between the landscape and the sky, we see the shaping process, which is the erosion. And even the erosion create deposits like sediments. And you see the sediments at the base of the different walls accumulating, indicating again the process of shaping. So in a geological map, all these processes should be seen. And actually, you see a geological map to the left here on that region, in the Dolomites again, and you see that with different columns, with different polygons, you actually see the different geological units, and they are superimposing one to each other, as you see in the stratigraphic chart to the right there, and they should be well distinguishable from unit to unit in the field, so they should be recognizable. They should have a clear stratigraphic sequence, one on top of each other or laterally in contact, and they should have a clear lithological evidence. So I would say the grain size, the rocks, the composition, and so forth. These are the main principles for indicating a geological unit, and they are the main building blocks of the formation process. Then there should be the possibility to understand in a geological map the deformation processes. In the map to the left, you see some linear features that you see in the legend here that are faults and fractures that should be indicating in a geological map. By doing a section of the geological map, we can go to the subsurface and see the different faults and faults in the section. So from the geological map, it is possible to understand how the volumes are deformed underneath the surface. And this is an important point for geological maps, and it covers the process of deformation. Then at the end, we have the shaping process, which is actually the topography, the landscape, but also some deposits, the loose deposits that here you see with polygons with light colors and patterns, and even some morphologies that are typical of given processes like alluvial processes or gravitational processes, landslides, and glacial processes like moraines and glacial deposits. So the main question, the main results is actually that going through all this kind of feature in a geological map, it is possible to understand how a landscape was formed by this, the position on different units and then placing different units, how it was deformed in time, and how it was shaped. So we can understand and explain the story of a landscape in terms of geological evolution, and also we can understand how the different units are in the subsurface. That's why it's important for the resources, because we can understand where they are, how they formed, and how to find them. So is it possible for planetary surfaces? Can we do the same from planetary surfaces? I would say there are many difficulties to make geological maps of planetary surface closer to the Earth geological maps. The first one is that many planetary bodies are actually characterized by impacts. Impacts. So we have meteoritic impacts that shapes and form a crater of different diameters in few minutes. We have a simple crater, you see to the left, they are bowl-shaped craters, and craters with a peak inside that are the complex craters. And to the right, you see a model, and you can take into consideration the time that make possible such craters. To the left, it's the simple crater, to the right, the complex crater. So you see here, the simple crater is formed in a couple of minutes, even less, for 2 kilometers of diameter, or 4 kilometers of diameter. For 30 kilometers of diameter, for example, a complex crater is formed in a little bit more, but we are still talking of minutes. And during this kind of process, we have all the many processes that takes millions of years for most of the geological process that we see on the Earth in just a few minutes. So we have the it deforms and shapes, shaping the deformation during the production of the crater itself, and even the deposition of loose material all around. So we have it forms, it deforms, and it shapes in the same moment. This makes things very complex in planetary body where we have no much screening effect of impacts. and where we have the record of impacts through time, through the geological time. Another point that make difficult to create geological maps on planetary bodies similar to the Earth one is that most of the geological map on planetary bodies are made from orbital data. So most of the geological map on the Earth are done going to the field so that we can recognize different geological units and lithology from one place to another, just going to the field. And here you see to the left some places where there are the outcrops that are in a, I would say, darker color here visible, whereas to the right, you have just the photo interpretation. And most of the photo interpretation is just based on the morphological characters, so rough units, smooth units, possible morphology of rims or ejecta of the crater. You will do a training on that when you will map, for example, Mercury. And you will see that most of this kind of photo interpretation is not based on lithology, but morphology and eventually morphostratigraphy, if you are able to understand the superposition between different units. So the frontiers of geological mapping on planetary surface is to get closer to the Earth geological units. And in order to do it, the main point is to integrate the composition information taken by spectrometers or the imaging spectrometers or even gamma ray spectrometers, the compositional informations in terms of mineralogy and chemical composition, and integrate this information to the morphological or morphostratigraphic ones. And here you see an example in which we see a Tchaikovsky crater and complex crater that you see there with smooth and plain and walls, with a nice morphological map to the right. Then we see color maps and indexes indicating the mineralogical composition and the integration between all this kind of information that give you not only the I would say mapping of the planet, but even the story of the infilling story, volcanic infilling story of the planet, of the landscape itself, like the Earth. So we see clearly that here we can understand the geological evolution because we were able to integrate the morphostratigraphy with spectral indexes, so with the mineralogy, with the composition. So this is for sure frontiers for geological mapping in the future. We need to work on multiple data sets, both related to mineralogical composition, elemental composition, and the images indicating the morphology. The other, the same, I would say, main goal can be now faced using the artificial intelligence and collecting all the color maps, them, spectral indexes all together in order to have a automatic or semi-automatic classification of the territory. And here we see an example that it is from Vergara et al., and she will explain you her work during one of the seminars this week. But the most important thing is that you see Wright et al. 2019, the morphological morphostratigraphy map that is quite well produced by the classification effects from AI to the right. And in addition to the lower right, you see even some additional information that are their composition information that can be overlapped to the morphological map that can be retrieved. So I would say if we are going to integrate compositional and morphological information all together and multiple data sets, for sure, artificial intelligence will be very important to the sake of this goal. The other point is to understand better the deformation, so the second process. And to understand better the second process, it's important, again, to integrate multiple data sets. In this case, the interpretation of the surface with the radargrams, for example, that give us the information of the strata beneath. And here you see a map by Costa et al. 2024 of the polar cap, now polar cap of Mars, in which we can relate the stratigraphy that we see on the surface and the geological map with the radargram beneath the surface and create a geological section as the geological section that we have seen for the Earth. We can do the same even without radargrams, but using craters as boreholes, as logs into the subsurface of the given area. And from the geological maps and the craters, it is possible to retrieve geological sections, as you see there, or even through different in-series geological sections, we can retrieve 3D geological models. So we can understand the deformation processes and how the volume of rocks are underneath the surface, because this is actually the second main point of a geological map after the understanding of the stratigraphy and deformation. And finally, we can go even on the field for the future and creating nested approach for understanding and making geological map directly from the field. So this is when we have rovers making traverses on given sites so that we can go from orbital images and understand the orbital images, relate them to outcrops, to produce a geological map that definitely is very, very similar or identical to a Earth geological map. But to go to the landing site, we need even technical maps that take into account the risk of landing and trafficability by understanding the slopes, the roughness, the solar illumination and different conditions, and the boulders. So another way for going close to a geological map on the Earth are actually the maps that relate to the landing site and the traverses and the panoramic views. So in conclusion, any geological map should provide information on the evolution of given landscape territories in terms of formations, so the formation of the units, deformations, how they deform from different kind of processes, and shaping of the units, how they can be eroded and modified through time. Then, for several reasons, this kind of geological map, like the Earth ones, are quite difficult. And in particular, the main reasons, in my point of view, are the dominance of impact cratering in the surface of many planets, and in particular, the general lack of in situ information. So we have no field checks, field observation to support the geological map most of the time. Anyway, the attempts for the future planetary geological mapping will be the integration of morphostratigraphy with compositional information and the understanding of the subsurface information, integrating them with other data sets like radargram. And everything can be done with the help of artificial intelligence and 3D geomodeling, so the modeling that allows us to understand the subsurface from the surface informations. The other point is to produce more high-detailed technical maps, including observation from the landing site and the traverses. And with that, I have concluded, and I open to potential questions.